that you normally won't find out when you write code or even when you run it, but these analysis tools, they help you do that. The first thing that we'll be looking at is static analysis. First of all, how does it work? Every time your code is compiled or interpreted, it goes through a process. First, the syntax will be checked, and then it will be converted into a form called AST, which is short for abstract syntax tree. And only then will the compilation or interpretation will take place. Now, with static analysis, what these tools will do is that they won't compile, but they might go up to that AST part to try and make sense of your code. And by doing so, they will try to recognize anti-patterns, like is a variable initialized? Are you using constants to denote string literals, or are you hard coding string literals? And by looking at those, they will produce a bunch of warnings, which you can use to make your code better. For this session, we will be looking at free software called SonarQube, which is a static analyzer. Let me open that. Okay, so I already ran some analysis, but we will do it again for the sake of this presentation. This SonarQube software has two components. One is the web component, which you can self-host if you like, or you can use a hosted service, and that's what's running in this window. And they also provide a CLI tool, a command line tool that you can use to run the analysis part locally on your machine or on a CI, and then send that analysis to this web part to provide a nice report kind of thing for you to look at. We will run that now. I should have it in my history. Okay. Now this command, it's available in their documentation. I have just copy pasted it, so you can look at it if you like, but I'll explain what's going on here. The source code is available in the current directory. This source code doesn't belong to me. It's an online feed reader that I use. So what this command does is that, as you can see, I'm using Docker to run this tool. So what the first command does is that it will copy the source code into that Docker container. If you don't know about Docker, don't worry about it. It's just a way to run tools without installing it, or an easy way to run tools. And then this is the project key. You have to, it's like creating a new list or something on this platform. You have to create a project and you will get a project key for this. For our tool, Miniflux is the project key. I mean, for our project. And then you mention the URL of it, and then they will give you a password which you have to pass in so that you can upload stuff to it. I have stored it in an environment variable. It's so that like I don't have to publicly show off my password. And when I run this, it will look at the source code, prepare a report, and upload it to the server. Okay, so let's look at the report. So as you can see, there are a bunch of things that this tool thinks that can be better. Some of these flags are false positives or even unnecessary. Like I remember seeing something about function complexity. There it is. It says that like there's too much stuff going on in your function, so try to simplify that so that it will be easy to make sense of. But like you can ignore those things. It's okay. But there are other things like define a constant. So this is a web server, and this is the path of a URL. So this is a valid suggestion because when you don't want to make mistakes while typing the URL, if you have it defined as a constant, you can use that constant everywhere else on your code, wherever you require to do something in this path. That way, like if the URL changes, you make the change at one position and it will be reflected in all the places that you're using the constant. By not doing so, you could cause errors in your program if the URL changes. So that's a valid suggestion. Now, running this tool, you should run this tool every time you make changes to your source code. Running it manually isn't feasible. These days, people employ a development process called CI/CD, which is short for continuous integration, continuous deployment. Popular code hosting services like GitHub already provide it. If you can afford it, you can also self-host your own platform. I'm using GitHub. I'm not using this particular tool because it doesn't support my language, but I'll just briefly show you what CI/CD looks like. So this is a project that I'm working on currently. I think I have some changes in here somewhere. So I have made some changes to the project that you just saw, and I will commit it to the repository. Committing is the process where you take a snapshot of the changes so that if you screw something up in the future, you can go back to the previous commit and start fresh. So let me commit that. As soon as I upload the changes to this service, it will start continuous integration, continuous deployment workflow, which you can see here if you like. I'll send this link. This. You can do a bunch of stuff with CI/CD. My particular configuration will check if the code compiles, and then it will run some unit tests and integration tests. It will upload the documentation and do something known as code coverage, and then it will exit. You can plug that static analysis tool into this configuration so that every time you make a change, it will be run and you get fresh reports against every commit. So that's something nice to know. Moving on, where is it? Let's look at dynamic analysis. Now, dynamic analysis is more effective than static analysis because with static analysis, it just looks at the source code and it might catch a few of the bugs, but it's also possible that it will let certain things slide. But with dynamic analysis, your program will be run and errors will be detected in real time against your code. So obviously this is better than static analysis. But one thing that you should know is that dynamic analysis, at least the kind that we will be looking at, we'll be looking at dynamic memory analysis. It's only useful for lower level languages like C, C++, Rust, and Go. These days, we usually write Java, Python, and JavaScript, and they are in those languages, memory is automatically managed for us by the garbage collector. So the memory analysis in those regions, it's not something that we are required to do. Those things will be managed by the people writing the garbage collection code. That said, if you ever find yourself in a position where you have to write low-level code, then this knowledge will come in handy. So as I said, the code will be run, and then if the tool detects any errors, it will be shown to you. The tool that we will be looking at is called Valgrind, and the way it detects errors is that it will run your code on a virtual machine, and then it will monitor every single instruction that is being executed. So if it smells something fishy, it will alert you. Now, before we discuss this concept, you have to know certain things about stack and heap memory. Generally, when we write code in higher level languages, we don't have to deal with stack and heap because everything resides on the heap. And you also don't have any choice. You can only allocate stuff on the heap. But with lower level languages, you are provided this choice. I think we have already discussed stack and heap memory in the class, but this should be a refresher. Heap memory is slow because the way it is allocated. I'll enlarge this figure. So let's say we require some memory, and this is the first block is the initial state that we are starting with. Initially, everything is free, and then we're requesting for 3 blocks of memory. So the system will allocate 3 blocks for us, and then we do some computation, and then we realize that we're done with the second block and we no longer need it. So we free that memory. And finally, we end up with this state. Now, the problem with this state is that unless and until some other program or even your own program is requesting for just 1 block of memory, this second block will be useless. It cannot be allocated anywhere. And this problematic state is called fragmentation. Because of, it's possible to fragment, right? And because of that, allocating on heap memory is expensive, because like every time you request allocation, the OS will do some computation to make sure that this fragmentation doesn't happen often, because if it happens often, then you're wasting resources. So that's why it's slow and it's unmanaged if you're using a low level language, and because of that it can leak, and we already saw fragmentation. Next, moving on to stack memory. Now, stack is a very simple data structure. If you want to mutate a stack, you add things right on top of it. This stack is inverted, but don't worry about it. So it's crazy fast. And it's limited because of the way this data structure works. You can only add stuff on top of it, right? Like with heap memory, you can do things like nodes or trees, but with stack, it can only grow in one way. So the operating system limits the size of the stack. On modern Linux systems, it's limited to 8 MB, and I guess on Windows, it's limited to like 1 MB or something. And it's automatically managed because there's just one way to grow and one way to decrease in size. So every time you call a function, let's say at this point, you're calling a function called foo. Foo will be loaded on top of this 0th element, and when it's done executing foo, it will be popped back out. So it's automatically managed for us. We don't have to deallocate or do anything like that. Before we move on to Valgrind, this is one more thing that we should discuss. It's not relevant to this session, but it's something that's nice to know, and that's performance. Like when you should use stack and when you should use heap, if you have the choice. Let's see that. So I am not a C programmer. I write code in a language called Rust. I'm sorry. So I wrote benchmarks in that language. Is the text on screen visible? Can someone's reply?
Yes, Arvind, it's visible.
Thank you. So first we will look at 2 functions, str and string. So in Rust, because of the way this code is written, I have to explain this part. In Rust string, there are 3 types of string. Over here, I'm just dealing with just 2 types of string. One is called a string slice, and that's the stuff that you're seeing here. And the other thing is called just string. A string slice is a part of a string. So its size can be computed at compile time. And whenever data type size can be computed at compile time, that stuff can be stored on stack. And if it cannot be computed at compile time, you have to put that stuff on heap, because you can only add stuff on top of the stack, right? And if you want to grow something that's already there on the stack, it will be expensive. You have to move all the stuff. If it's in the middle, you have to move all the stuff by whatever size you required. So that's not feasible. So you put those things on heap. And so this is heap allocated, and this thing stays on the stack. And we'll see how the performance of both of these things differ. To do that, I will run the benchmark. So the stuff on the stack ran at 53 nanoseconds per iteration, and the one on the heap ran at 1038 nanoseconds per iteration. So there's like a 20 times, so the stack is 20 times faster than the heap. But there is a catch with stack allocation though. So if you remember, I told you that every time a function executes, it gets put on top of the stack, and when it's done executing, it gets popped back out, right? So if you're trying to return some data, where did it go? We're trying to return some data, like for instance, in these functions. Yeah, so the create in these functions, I'm creating an array of integers of size 1000, and I am returning it to whichever part of code is calling it. I'm calling this function from within this function, so this array will be returned to this function. When this is happening, uh, the function will get popped out, right? So whatever data that is being returned should be copied, and it should be sent back to the previous layer in stack. So there's an allocation going on, and this stuff can be expensive on stack. Whereas in the case of heap, you are just returning a pointer to wherever it is located on the heap. A pointer is super small. It's probably only 2 bytes or something. Like, I don't really know. It's super small. So rather than returning something that's 100 elements large, you will be returning something that's only 2 elements large. So we will see how the performance differs between returning large elements from stack and heap. Let me uncomment those things. Generally, when returning stuff from functions or when you want to put stuff on the stack, you should try to limit to 1 kilobyte of memory. If it exceeds 1 kilobyte, then it's better that you put things on the heap. That way you get the best performance. So, so these were the two functions that we were benchmarking. The stuff on the heap is 3 times faster than the stuff on the stack. So that's something that's nice to know. Now let's go back to Valgrind. Valgrind. There's one thing though. The first time I heard about Valgrind, I thought it was pronounced Valgrind because it has grind in it. But I recently learned that it's pronounced Valgrind. So the least that you can do for a tool that comes free is to pronounce it the way the authors wanted it. So Valgrind. Where is it? So the way we will be looking at Valgrind is that I will first compile this code and then I will run the executable to see if it has any visual side effects. I mean, this code is buggy, so we should be seeing visual side effects, but it's also possible that they will go unnoticed. And then we will run it through Valgrind and we'll see if Valgrind can detect the errors. And then if necessary, we will use a debugger on the code. The debugger that I'll be using is GDB, which is short for GNU debugger. So firstly, we will look at a particular error called seg fault. Seg fault is short for segmentation fault. It happens when you are declaring a data type and you're not initializing it. I mean, you're declaring a variable and you're not initializing it. So when you're not initializing it, at least in C, it will be pointing to garbage value. And the operating system knows that you don't have any rights to access that memory. It could be anything, right? It could be from, it could be the memory from the previous execution or something. It's just something that you don't have authority to access to. But we are accessing it. And when we access it, it will cause a seg fault. Normally, the operating system should detect this and it should stop execution altogether, but we'll see what happens. So for compilation, I wrote a make file. A make file is it's just a simple way to run multiple commands during development. So I'll remove this flag for now. All it does is that it will compile main.cpp and it will output a binary file called x. Let's do that. Yeah. I think the compilation was successful. Anyway, let's run this. If you remember the code, we shouldn't be getting any values because we didn't assign anything to it, right? But we are seeing something here. And if we run this code, run this binary again and again, we should see random values because it's garbage. Each one of these values are different because they're garbage. We cannot tell what the next thing will be. But the operating system did not stop it, which is surprising. But okay, we'll run this through Valgrind and see if it detects it. So Valgrind, like I didn't even tell you about this. So Valgrind is a framework, and the tool that we are looking is called memcheck. Valgrind has lots of other tools like Hellgrind, Cachegrind, and a bunch of other tools. Memcheck is the tool that will detect memory errors. And it's also the default tool. So if you're running any other tool, you'll have to pass a tool flag with the tool name. But since it's the default, we won't be doing it. So everything all right? Ah. I don't really know what's happening. Let me change this to an array and we'll see if that flags it. Okay, it appears Valgrind is not detecting this. That is weird. Let's see if sanitizes. I can't spell today. This is weird. It should be working, but I don't know why it's happening. Okay, no idea. I will get back to you later about that, but for now, let's just move on. This is embarrassing. So the next vulnerability that we're looking at is Stack Overflow, Stack Buffer Overflow. Stack Overflow is different. It's when you have some data, some variable with a fixed size, and you're writing at a point that is beyond that size, and that's what we're doing here. We are allocating, we're creating an array of size 10, and then we are trying to write more than what this variable could hold. So let's do that. Yeah, so the operating system was able to detect this error. It says that stack smashing is detected. It's when you're trying to write, it's a stack buffer overflow, and it aborted execution, which is cool. So now let's try to run the same thing through Valgrind. So even though it's printing some errors, Valgrind is not useful in this scenario because Valgrind is useful only when you're dealing with heap memory related errors, and this stuff is on the stack. So while it can show you that it can show you the position where the program terminated, which is at line 18, it doesn't really know what caused the termination. So to deal with these kinds of errors, you compile the code with a sanitizer that was recently included in the compiler. And what the sanitizer will do is that it will include some additional code into your binary, and which will monitor all the data that is being allocated or used. So we'll compile the binary again, we'll compile our source code again and run the binary. This is all the doing of the sanitizer. It knows that we are trying to access some illegal memory, and it will point that thing out. We'll go through the output line by line. So we have a stack buffer overflow at this address. This is the address of the memory, and it says that we've tried to write 23 bytes at this address location when only this much is permitted. So our variable foo has got is from byte 32 to byte 42, but we are trying to write something that's 23 bytes. So that's illegal, and it shows us a nice pictorial representation of what we're trying to do. It doesn't matter. So we know that we have a stack buffer overflow, and let's try to fix this. Okay, one more thing before we fix it. In this scenario, there were some visual side effects. We knew what was happening, but this thing can also go unnoticed. That happens when you have something that that's on top of this variable, or when this isn't the topmost element on your stack, your OS can detect that there is a stack buffer overflow, but you have something right on top of this thing, and you have you're authorized to access that memory, that region of memory. Then the OS will have no idea what's going on. It's legal, right? So let's try to do that. What's happening here is that we are creating another array of the same size, and we are writing the same string to foo. But this time, hopefully the error should go unnoticed. I'll remove the sanitizer is clever enough to detect that. So for the case of this illustration, I'll remove the sanitizer. We'll compile it and then we'll run it. Okay, so I guess I have to reduce the size a little. Come on. Okay. Now, I also try to print bar. The ideal behavior is that there should be nothing in bar and we should be seeing garbage values, but we'll see what happens. Okay, there's nothing. Okay, so there should be nothing in bar, but we are seeing something here, and I believe this is the extension of the string. Yes, we are seeing this part of the string overflow into bar. So you can imagine if we have such vulnerabilities in our code. Our code contains errors, but it will silently corrupt memory, and all these kinds of behaviors will be put down as undefined behavior or general application instability. These things are just a huge pain in the ass. But if we pass the sanitizer flag, hopefully this thing will detect. Sanitize address. It should detect. It's fine. Okay. We get the same error from the previous run. It detects a stack buffer overflow. Also, one more thing, this sprintf function, right? What it does is that it will take a buffer, a string buffer, and then it will try to write whatever data that we are passing in the third and all the other arguments that like you can have n number of arguments after this. It will try to concatenate all the strings and it will try to put it within this variable. This is problematic because it doesn't care what the size of this variable is. So there is an alternative function called snprintf. And what this thing will do is that it takes an extra argument which you can use to tell the function about the size of the buffer. So if I pass in buff size here, it should be fine. So even though this string is longer than what a variable can hold, it will write only this much amount of data into a string. So with that, hopefully we shouldn't see any errors. So there are no errors. And I'll even turn on the sanitizer flag. There are no errors. So that's something that's nice to know. The third type of error is memory leak. You must have noticed in browsers or any memory intensive location that if you run it for if you have been running it for some time, it will hog all the memory up and your system will run out of memory. Those situations are called memory leak. It happens when you're trying to allocate some memory leaks only happen on the heap. So when you're trying to allocate something on the heap, but you're not freeing it after you're done with it, you lose the handle to that memory, right? Our handle to the heap allocated memory is this thing called foo. And after this curly braces, you lose the handle. You can no longer refer to that region of memory. So if you're not freeing it, that situation is called memory leak. And let's see if Valgrind can detect that. We'll compile it and then we'll run it. Okay, I'll turn off the sanitizer. So there are no visual effects because it's normal behavior. The OS cannot detect it, but Valgrind will detect it. So it says that there's definitely a leak of 80 bytes. There is one allocation and 0 bytes. So at exit, when the program terminated, 80 bytes was still reachable. So the way you fix this is by freeing that memory. And you do that by calling a function called free, and passing in that handle. This should fix that. I'll run it straight through Valgrind. All heap blocks are free, no leaks are possible. We have one allocation and one free, so that's how you deal with memory leaks. Freeing is one thing, but there's also double free. It happens when, in this section of the code, you can see that there's a double free thing going on here. But when you have a bunch of statements between where you're freeing, where you're allocating and where you're freeing, it's possible that you could get confused and you commit a bug like this. And double free is illegal. Let's see if we'll try to compile this code and see if the operating system detects it. So the OS was able to detect this. Double free detected at this place. Tcache2 is the thread cache. So it must have ran on thread 2 or something, no idea. Valgrind. And Valgrind will give us a neat output of what's actually going on. It says that we are allocating at CPP, line 24, and then we are freeing it again at line 25. We are freeing it for the first time at 25, and we are freeing it again at 26. So with this output, you can debug double free. All you have to do is to remove the extra free statement and you should be fine. Everything's fine now. Invalid write. There were no visual effects. Let's run Valgrind. So before we look at the output, let's try to make sense of what's actually going on here. We're allocating some memory on the heap. We're allocating an array of size 10 on the heap, and then we are writing at the 11th position. In C, arrays go from 0 to n-1, right? So we are trying to write at nth position, and that's illegal. So Valgrind was able to detect that we're doing that. It tells us that we're trying to write something of size 4 at 9:30. This is a common mistake. The way you fix it is by going behind one pointer by doing this, and you should be fine. But let's just write it first position. I have no idea what's happening. So we're fine now. I think this last type of bug is kind of funny. I have no idea why this thing is even legal, because like when you're trying to allocate something, you mention the size as a positive number, right? But in this, but for some reason, malloc, the allocation function, can also take a negative number. And when it receives a negative number, it will try to convert it to a positive number. And when that happens, you will get a very large number and a very large chunk of memory. The OS won't detect this because you're just requesting for a large amount of memory. But since Valgrind is a virtual machine, Valgrind runs this code on a virtual machine, it can detect how much memory you're requesting from malloc. So that's apparently an error. I didn't know about that until now. Let's try to do that through Valgrind. Things were working when I first ran it. I'll just request for -1 and we'll see what happens. Okay. It tells us that we are trying to request for something of, we are trying to request a size in the negative, and that's fishy. That's how Algorithm puts it. And gives us an output of where it's happening. It's happening at line 36. Easy to fix. You just remove this thing. Now, okay, I'm not freeing it. Now everything is fine. So that's how you debug issues with Valgrind. Now, C and C++ are very old languages. C was written sometime in the 70s, and it's a very primitive language. Memory errors are very expensive. They can wreak havoc in your business. Modern languages like Rust will give you the same kind of controls that C and C++ do, and will also make memory management simple. In fact, Rust guarantees that it's memory safe. So if there is some bug like this in your code, you can blame it on the compiler without actually taking the fall for it. So that's nice.